Okay, good afternoon. So today, so the agenda for today is mainly so three things. I want to go through some of the logistics because there are quite a few of them. Your kind of quiz is coming up, so we're going to talk a little bit about that. Then I'm going to spend most of the time of this lecture on reviewing things that we have discussed so far, especially things after forwarding, because this is kind of like the most confusing part of this class, this few weeks, because you kind of like add things and then kind of consider various different options. Excuse me. So you quickly can get confused. So we're going to help you a little bit here by kind of reviewing and giving you the big picture and then kind of like comparing different options. So hopefully that helps. And then if you have more time, I'm going to start the branch prediction part, continuing the branch prediction part, to help you kind of not being confused of which part would be part of your quiz and not. I put everything about the new things on a different lecture, lecture 9. And basically this will help you that everything I said in this lecture 1 to 8 would be part of your quiz. And then everything after lecture 9 and so on would be part of your quiz too. Okay. So first of all, let's talk about the computer assignments. I've seen many of you already kind of submitted and got the full grades. That's great. Those of you who didn't, don't worry. Some of you might need more time. Some people know already how to do things. Some people might need more time. So yeah, use the time to kind of like design your project. We are here to help, so make sure to kind of utilize the office hours for the TAs and myself. I've seen lots of activities on CampusWire as well. Continue doing that. That's totally fine. And the important thing about the project is actually very helpful for your quiz as well. So that's kind of like we make the timing such that as you're working on your project, you are essentially kind of also studying for your quiz. So hopefully that helps. So one thing that caused a lot of confusion was this difference between kind of the types of files that we provided to you. Honestly, if you kind of like, read the project description thoroughly and kind of in detail, you shouldn't have questions, but let me actually see if I can maybe help you a little bit with that. So if you actually go to the files, you will see that we're kind of providing you 3 different files, okay? There is this .s files, right? There is this .txt files, and there is this intsmem files, okay? So what are the difference between them, okay? So let me do, so and then there's 3 types of them. There's R type, there is SW type, and there is all type. So, okay, 3 and 3, so 9 total files. So let me focus on the S types, and that kind of, it's kind of like, helps you to, let me see if I can open it in some way. I can't, I think. Let me open this one. So the S type, okay, so I couldn't open the S type here on the Google Drive, but the S type is basically just the left column, okay, the leftmost column, which is just the assembly instructions, okay. It's a sequence of instructions, and these are the instructions that it does. The difference between this 23R-type.text and 23R-type.s is that this R-type.text is more information. They are the exactly same things. They're just more information in this file compared to the other file. So this one has the same assembly set of instruction, but in the second column and the first column, what you're seeing is the PC address and the binary version of that instruction, right? So this is the machine, the one you see, not the binary, the hex version of the code. So you see what you see in the middle is basically the machine code. The left side is just the addresses, and the right side is the actual instructions, okay? And then the comment in the end is kind of helps you to see what would be the outcome of this. So in this particular case, A0, which is your X10, would be equal to -8, and A1, which is your X11, would be equal to 23. So this will kind of help you to debug, okay? But these are just for your information. Your code does not need to read the .s file or this file, okay? You can just ignore these files. This is just for you to kind of understand what these files are, okay? What you need to kind of feed into your to your memory, to your code is this file, okay? So what is this? This is what happens in your instruction memory, okay? Each line is a 8-bit value, 1 byte. I'm showing it in an unsigned version. So if you translate 147 to an 8-bit value, that is the value going to be loaded in the first line of your memory, okay? The second line would go to the second line, the third line goes to the third line, and so on and so forth. So this is basically what is loaded into your instruction memory. Each line, 1 byte, okay? And of course, 4 of them together would be 132-bit instruction. And then again, if you look into the first 4, if you translate that into the binary, you will see that it's actually exactly the same thing as you're seeing here in the R-type text, okay? So that second number in the middle, the 001000093, that's exactly the same things happens. It's divided into 4 numbers and goes into your instruction memory, okay? So this is kind of what's happening. So your code does not need to read any of these. The only thing that it reads is automatically reads this. You have to just in your kind of terminal say that this is the name of the file that you're reading, okay? And actually, if you go to your code, you will see that the code is automatically actually reads this. So you actually don't need to anything regarding like reading this file, okay? Unfortunately, Google Doc doesn't load this, but essentially your CPU SIM already reads this into your INSMEM array. You don't need to do anything for this, okay? You just feeds the INSMEM file into the code, the binary code that you have compiled. It automatically reads it and put it into the INSMEM array. What you need to do is after this, that you need to basically, you need to basically just read these 4 instructions at the time and do something with it, okay? That's kind of like what you need to do. Any questions about this? About the INSMEM? Are we clear? Okay. The second question is, how do we test? So I provided kind of like some files for you to test, right? If you upload your code into Gradescope, you will see that there are 2 tests. Test 2 is essentially that all file. So if you locally, pass that test, your test 2 should be passed as well. This is just a sanity check to make sure that your code runs. Test 1 is more elaborate. Test 1 has a bunch of different corner cases and so on. I also shared the assembly code of test 1 on CampusWire. I didn't provide you the INSMEM version of that. I just provide you the assembly. The reason that I did this was for you to kind of also do a little bit of work of creating your kind of test set and test setup. And the reason for that is kind of like mimicking what you would get in a normal Word, where nobody going to give you test setups, nobody going to give you tests. You have to start from scratch. You have to create your own, software. You have to come up with your own tests and everything, okay? So most of you are going to graduate soon. And when you're joining a company, none of these things that you're doing in classes is in real world happening, right? So like coming up with good test strategy and good corner cases is part of, being a good software developer, right? So I want you to kind of like do that a little bit as well and practice that. But there are things that you can help yourself to debug, especially given that you have the assembly code. My recommendation is that if your code doesn't really provide the correct output, kind of like go through the instructions and trace them and see what the problem is. Another big problem that I've seen is compilers and kind of like problems with interfacing with Gradescope. Since Gradescope is using an autograder, there might be some compiling issues. First of all, you can upload as many times as you want. Some of you have like questions of, would my code work on Gradescope or no, or what would happen and so on and so forth. Well, the answer to all of those questions is that you can test it yourself, okay? So just upload your codes, even if it's not fully functional yet. But in order to make sure that it compiles or not, you can just upload your skeleton code and see whether it works, okay? And see whether it generates some outputs. Although you won't pass the test, but if you actually look into the comments of the test, you will see that it's kind of, printing some value, okay? So you can check whether that value is what you were expecting to see or not, okay? One thing I see some of you had problem with was you were zipping your files and then uploading the zip file to Gradescope. If you do that, then that creates another subfolder in Gradescope, and the script will not understand this subfolder because you use random names. So it cannot compile your code, and as a result, your test will fail. So don't zip your files and upload the zipped version. Just select all of the files that you've created, upload them all on Gradescope, then the Gradescope will understand that and pass the test, okay? Yeah, and then I talked about debugging. So for some of you also had, for debugging, you can also like, if you test all of these things and none of them work and kind of you become desperate, you can always message me and I can check Gradescope for you, because on my side, I will see also the compile error messages. Unfortunately, on your side, you won't see it, but I'll see what's, and then you can always download your code and test it locally. So if like you test everything and nothing worked, you can message me and I can fix it for you. I already done it for most of you already. And then last thing is that those of you who are doing Python, unfortunately, Gradescope cannot kind of be configured for two different languages on the same kind of setup. So what I did so far is that I think there was one student who wrote in Python, and I just manually run it on my own machine and then see if it passed the test. If there are more of you who wants to write it on Python, I'll probably do the same, unless there are many of you who will do that. And in that case, I create another autograder just for Python. So there will be two kind of submission links. But is there in this class, how many of you are planning to do it in Python? Just raise your hands. Okay, not that many. That's okay. So you just message it to me. So if you upload it on Gradescope, it will fail. What I'll do is I'll run it locally on my own machine and I'll just adjust your scores, okay? Any other questions from CA1? Are we good? Yeah. Say it again. It's not, so the question is that the test cases I'm providing are not fully comprehensive. Yes, it's not. And again, that's the part that you kind of like, as a software developer, you may want to do. The good thing is that if you pass those two tests, you're technically fine, although there might be some very, very nasty kind of debugging, bug in your code. But if you pass those two tests, you're fine, okay? So you're already given kind of the test cases in some sense. You just need to be able to pass those tests. Does that make sense? Yeah. Say it again, like the last one. That's all. You don't need to change anything. If you pass the test, then you're set. Okay. So you also have a homework this week. So I mean, it's kind of like too much workload, I know. But again, it's kind of helps you for the quiz. In the past year, I see people rather to have the homework, doing the homework and be more ready for the quiz rather than not having it. But again, you can drop one homework. So if you don't have time to do it, then you don't have to do it. but it's very, very relevant to your quiz. So I definitely recommend to kind of spend some good portion of your time on the homework. And then another thing that I want to point out is that, you can check previous samples. What's going on with this computer today? Yeah, I don't know what's happening, but hopefully it works this time. Let's check out the previous samples, okay? If you go to the schedule, if you go here, this website, if you go down, you'll see this kind of like schedules in the bottom of your screen, if it actually decides to, yeah. So you see these kind of like two little links. This is for last year and previous years. All the solutions for all the homeworks and quizzes are there. So you can actually use them to kind of like, test your knowledge further if you want to. Okay. Any questions about homework? Cool. Class participation. So, I mean, someone says that if you can kind of do kind of half or hybrid version of CampusWire and class participation, you can, and I explained that in the first lecture. So you can be like 50% class participation and then cover that 20% with your CampusWire participation. One thing that I saw is that you're not really answering each other's questions except few people. Other people are just mainly just reading the questions, especially like these compile questions. Oh, what should I do with InSmem versus the S file and all those? I think most of you have figured out. So maybe you can actually contribute, right? So answer each other's questions, you get more points, and you that will satisfy your participation, right? And then if you're really active, I'm going to give additional 1% to the top 10 or 20% of the class who are more active on CampusWire, okay? So you actually will earn more points by just being active. So these simple questions, at least you can contribute, right? Don't be worried if it's wrong, okay? Because there's always, we can edit it, or we can kind of add more things to it. And again, your answer is also completely anonymous, so nobody knows who answered this. So don't feel shy or worried that you cannot, like, you know the answer, but you're kind of shy to write the answer. Do it, you'll get more points, you will get more bonus, and so on and so forth, okay? So be more active on CampusWire by asking questions, but by also answering questions, okay? Because the faster we can answer each other's questions, everybody can benefit, right? So if my question kind of sits there for 3 hours, nobody answer it, I'm kind of wasting 3 hours of my work. Versus if somebody within 5 minutes answer my question, then everybody will benefit for that, right? So please do that. One thing I noticed is that people kind of waiting for me to kind of put the code and then kind of leaves out. So what I'm going to do is that I'm going to put the code at the beginning of the class, so you don't have to wait for an hour to kind of then leave. So honestly, the whole point is for you to come to the class and ask questions. If you think that this is not helpful for you, you don't have to stay in the class, okay? And then that 5% is mostly everybody gonna get it anyway. So don't just like come to the class and kind of hoping for the code to be released as soon as possible. That's not the point, okay? So this is the code. Wait a second. So let me see if okay. So the code is E6 QPWT5G. E6QPWT5G. I can close my eyes if you want to leave. How many bonus points will be on Campus Fire? So for now, I'm thinking about 1 point, like 1 additional % to your total grade. So higher the better, of course, to increase your chances. What I'm probably going to do is that I'm gonna like look at the top 10 percentile and then give bonus to them. But last year we had someone who got like 1,000 points or something, so I gave extra point to that person. Are we good? Okay, so a little bit of details about the logistics of quiz 1. So it's going to be in person in the class next week's Tuesday. We're probably gonna start a little bit later, so I'm gonna start maybe at 12:15 or so. So the first 15 minutes, if you're late a little bit, we can let you to kind of be late. But then we're gonna use the entire class for the quiz. The quiz itself will be about an hour and an hour and a half. So we're not gonna have an additional lecture. I'm gonna like post a very short video of like 30 minutes or so, in substitution of what we're gonna have in the class. So you just come to the class, do the quiz, and then leave. Okay. There will be a sign-in sheet that you have to kind of physically write your name. This is just for making sure that people in the class, like how many people are in the class. The quiz itself will be released on the website, so there will be like a link, same as your homework. I'll put the link and then you have to click on the link. There won't be any hard copy, so I'm not gonna waste like 250-ish, each one like maybe 10 pages or so of papers. So everything would be digital. I'm gonna display it here, so if you just come with a piece of papers, you probably can see it on the screen. But you can also bring a cell phone or tablet or a laptop or whatever you want and read it from there. You can write on your laptop as well the answers, or write on your tablets. You have to upload your answer to the Gradescope. So either scan it or create like a Word document or whatever, create a PDF and then upload it. Let me see. Yeah, 60 to 80 minutes, no paper copy. Everything from lecture 1 to 8, and this is lecture 8. The video for this part, if you have more time to talk about branch predictors, will be part of lecture 9. So I'm gonna like basically pause the video at some point today. And then lecture 9 and everything afterwards will not be included. It will be open book and open notes. So things that you're allowed to do is that you can bring anything you want, right? You can bring the book, you can bring any piece of papers, whatever you want. You are allowed to use any software or application or tools, okay? You can use calculators, you can use MATLAB, you can use, write a Python code to kind of calculate the answers. You can do any of those if you want to. You can search the internet as much as you want, okay? What you're not allowed to do is generating new content, and what that means is you cannot post questions on any of these websites like Chegg or I don't know, Stack Overflow, stuff like that. That's considered cheating. Okay, so if you find that, you will be reported. You're also not allowed to query these AI models because that's also considered generation. Okay, so you cannot ask ChatGPT to kind of give you the answer. You are also obviously not allowed to chat to each other or anybody outside the class, right? And then you cannot discuss either questions or answers during the class with anybody else. And after the class, of course, you're free to discuss it as much as you want, okay? The format for Q&A during the class is that I'm gonna be here, the TAs will be also here, at least 2 of them. So we're gonna kind of walk and then help to kind of So you can just raise your hand and we can try to answer your questions. If you kind of sit in the middle of this kind of row, one thing you can do instead is that just message me on CampusWire with your questions. I'm going to also monitor CampusWire, my messages on CampusWire. So you can just post a question on, like, message me. Don't post it on the regular kind of website, but just message me directly and then I can answer your questions that way as well. Message me instead of the TAs, that's faster, okay? As we have a bunch of CAE students, for them, what we're going to do is you can stay at home, okay, and join via Zoom. I'll share the links later. So CAE students, those who actually, have the cases approved and already received a CAE letter, those people can just stay at home. You don't need to be here. Just stay at your dorm or home or wherever you're comfortable, and you can join Zoom. You don't need to go to the CAE center. Just stay wherever you are, and then you can do it via Zoom. And this is only for CAE students. Anybody else, I will not allow people to be on Zoom. If I see it, I'll drop you, and then you will get 0 for your quiz. Okay. Just say, oh, I'm in Zoom and so on. If there's like a very, very special circumstances that you cannot be here, like, you test positive, etc., then we can work something, okay? But other than that, I'm expecting almost everybody to be here in person, okay? And another question that I have is if you need any other accommodations that is not part of CAE, but you think you need that, you can let me know. Just email me or message me on CampusWire. We are again here to help you and to make sure that you have the best experience, okay? So if there's anything else that you think you need help, you can privately let me know and then we can figure something out, okay? Any questions, comments about quiz? Are we set? Yeah.
If we have a question,
during the quiz, you can message privately on CampusWire. I mean, if you're kind of accessible, which means that you're kind of on the side of the rows, then you can just raise your hand and we'll come to you. But if you kind of think that it's like you're gonna speak loud or you're gonna disturb other people by asking questions, you can message me on CampusWire and I'll answer it on CampusWire. Yeah.
Are the questions going to be similar to like homework questions?
Yeah, so the question is, are the questions going to be similar to homework? Yeah, roughly the same, not exactly the same. So usually I kind of like add a little bit of kind of tricks, but other than that, it's mostly the same. Just expect that you have to be quick. So be ready to kind of know the concept. Don't think that you have lots of time to kind of go over the materials. But things that you want to quickly kind of review and check, you can always do with your laptop or you can take a look at the slides and so on. So, okay, yeah.
there shouldn't be any like programming.
The question is, there going to be programming assignments in the quiz? No, because I'm assuming that you can write it in a piece of paper as well. And usually what my experience is that writing on the tablet or laptop is easier because, for example, you can then copy paste kind of like the data path and put it there. So people who are writing it on paper usually have harder times. But unfortunately, since we don't hand out paper copies, that's unfortunately a little bit unfair to the people with paper. So that's something to consider. But again, we accept paper. If you're fast in drawing things, then you should be fine. Yeah.
Are you able to post solutions for homework 1 and 2?
We already, so the question is, are you going to post the solutions for homework 1? And we already did that on CampusWire. If you go through the pin post, you'll see that. For quiz, for homework 3, we're gonna do it on Monday morning, given that the deadline is Sunday night. But yeah, all the solutions are already there. The last part of the logistics is office hours. So I just want to remind you that we have office hours on Fridays, Mondays, and Tuesdays by the TAs. The times are posted on CampusWire. Use them this week if you have a problem with the CA, compile problems, I don't know, like debugging problems, etc. My own office hours are also on Thursdays, in the afternoon. So use those if you need it. Okay. Okay, any other questions, logistic wise? Yeah.
If you're doing it on paper, can you just come with pre-printed like copies of the data path?
Yeah, the question is, if you come with the paper, can you come with a pre-printer version of data path? Yes, you can. As I said, you can bring anything you want. So if you can kind of like, predict that what type of like, I mean, because we have a bunch of versions of the data path, right? So you may want to print all of them. But I'm personally hesitant to use lots of papers and waste lots of papers. So yeah, I don't know, like maybe practice to draw them fast as part of your preparation. Yeah.
We allowed to use your slides, like just have a PDF of in case you want to like.
Yeah. So the question is, can we use the slides? Yeah, you can use, as I said, you can use anything. And as I said at the beginning, if you remember, you can watch the videos too. So you can use anything, literally. Yeah. Bring the book or your slides, that's fine. Okay. So let's review kind of things that we have learned so far. So I'm gonna kind of like, kind of talk about this a little bit. So if you remember, like, the first week we kind of had some kind of history lesson, but then kind of the real things begins when we start talking about the role of the ISA, right? And we said that essentially the first step in designing a processor is kind of defining the ISA. And then we kind of like talk in length about this table, right? Different type of ISAs, operands, commands, difference between them, memory, branch and control flow instructions, and so on and so forth. So this is kind of like, this table is your friend to help you to kind of understand this. If you still have doubts about any of these questions, any of these instructions, now it's a good time for you to review these kind of things. But I think homework 1 and project 1 kind of helps you probably a lot with kind of understanding this. The next step that we did was moving from ISA to machine code, and we said that we're going to use a standard table for RISC-V, and this was kind of the table that we looked at, and we said that essentially we have different types of instructions like an R type, I type, S type, B type, J type, and each one is kind of like have different types, like, there's an opcode, some of them has RD, some of them don't, and so on and so forth. And again, probably during your design of your computer assignment, you probably like very, very thoroughly look into this table, because there's kind of like different ways that you're decoding this. Again, if you have doubts and questions about this, let us know, and we can help you. So this is kind of like the most focus of our homework 1 and project 1. Then we talked about the execution model, right? So saying that, okay, now we have the machine code, now what, right? And we said that essentially what we are doing is that we are loading this machine code into the memory. Essentially in your CA1, this is your instmem code, right? So this is the instmem file, the text file, which we load into the memory, and then loading into the memory essentially in your CA was basically reading this and writing it into some form of an array. And we call that kind of an IMEM or something like that in your code. And then afterwards, we were basically designing this, right? So the question becomes, how do we design this kind of right part, which is the CPU, right? So the rest of our kind of focus was designing this kind of part. So we kind of like fix these issues. So we kind of like focus on this. And then we gave you this kind of big picture of basically what we have is a combination of 3 parts: a controller, a data path, and the main memory, right? So far, we really didn't discuss much about this part. That's going to be what we're going to discuss later in the class. Once we are finishing with, like, next week, once we finish the design of our CPU, then we're going to mainly focus on the main memory. And you're going to see that this main memory itself is kind of layers, has tiers, and so on and so forth. But this is kind of like the idea. And then we kind of go through in detailed description of how do we come up with this design, which was basically, this was your kind of CPU, right? Which was combination of these blue parts, which was your controller, and this black part, which was your data path, right? And again, this is the part that you've done in your CA1 and in your homework 2. So hopefully those 2 things is helpful in kind of understanding this. And another thing I want you to kind of make sure that you understand it correctly is what changes do I need to make to support a new instruction, okay? Because what we do is that we always start with the core and then we add things to it in order to support more instructions. In real world, that's how it works too. So I want you to be able to, for example, if we give you a arbitrary instruction, be able to kind of add the data path such that you can support this. And the supports, whenever you are kind of thinking about how do I go about changing the data path to support this new instruction, you have to always think about the minimal amount of changes. The less invasive, the better it is. So like, for example, I can add another register file, for example, to fix some problems, but or versus I can add just a mux to kind of fix the problem. And of course, when you're comparing these two solutions, this is much more better solution because the cost that associated with this supporting this new instruction is much less. Okay, so so always go for something that is the minimal, absolute minimum amount of changes that you need to the data path to support instruction. Okay, so that's another thing that I want you to remember. Then we also talked about the data flow. That is, for a given instruction, can you calculate the data flow and the associated delay with it? So for example, for load, we said that essentially the path would be something like this, and then coming back here. And then another path is, for example, from here to here, and so on and so forth. And then you kind of need to kind of compute the maximum of these paths, and that would be the delay associated with load. And then if you repeat this for example, other instructions such as add and store and so on, you will find different delays, right? So calculating this is important because it helps you to understand how your data flow works, right? What are the units and which one is which? There are a whole bunch of good questions in CampusWire about how do we calculate the delay for muxes and gates and so on. I recommend you to kind of read them and follow them and make sure that you fully understand them. Okay. Once we kind of finished with our single cycle design, then we talked about how do we improve this, right? And then as I said at the beginning of this class, most of the things that we are talking about is all about improvement of an existing baseline. So in order to understand what we need to improve, we start with this iron law, this kind of fundamental rule that we use in order to compute the CPU time. And I told you that essentially what I want to do is that I want to minimize this, reduce this as much as possible. And in order to reduce this, I need to reduce some or all of these different parameters, right? The instruction count, the CPI, and the cycle time or CT. And this one I said that is essentially mostly out of the control of a computer architect, but these two are kind of usually controlled by a computer architect, especially this one. And this is the one that we focused a lot so far. And then we're going to continue focusing on this part. For a single cycle design, basically your IC, your CPI is always equal to 1, and your cycle time is the time, the maximum time takes for load instruction, usually. And this is how we kind of come up with this numbers. And IC depends on the algorithm, right? So whatever algorithm you're using, this IC will reduce or increase and so on and so forth. So once we kind of come up with that, say, okay, how can we improve this? And we propose the idea of pipelining. So for example, if initially I had this, which was basically, for example, the delay of a load, that starts from PC all the way to my register file, I propose that I can add pipeline registers in between. So I basically break this down into designs like the one that is below them. So if I add one pipeline stage, I basically breaks down this, let's say I just divide it equally in half. So what will happen is that each of these parts would be T divided by 2, because now I divided by half by adding this additional pipeline register. But what is happening is that although my latency is still T, my throughput is increasing by a factor of 2. Why? Because now I can run instruction 1 here, and I can run instruction 2 here. So I can do 2 things at the same time. I can overlap things by adding the pipeline registers. Here I could only do in the top one, I could only do instruction 1, but now I can do half of instruction 1 and half of instruction 2. So if I look at my throughput, I'm essentially increasing my throughput by a factor of 2, and as a result, I'm speeding up my processor by a factor of 2. And then if I continue doing this, I get like if I add 3 pipeline registers, I increase by a factor of 3, and so on and so forth. In your design, we said that we're actually adding 4 pipeline registers. In other words, like dividing this into 5 pieces. So we are kind of essentially can speed this up by a factor of 5. We also discussed that why don't we go further than this? And if you remember, I told you about this concept called diminishing returns, which means that the more pipeline I add, I really don't make this equally divided. But what I'm really adding is extra power and extra delay, because these registers essentially adding a little bit of delay. So it doesn't make sense to go beyond certain numbers. So that's why we kind of like stop at 5. Okay. And then, so what we did was kind of like, design your processor based on this. So we kind of say that, okay, we call this instruction fetch, we call this instruction decode, or ID or D, we call this EX, we call this execution stage, we call this memory stage, and we call this write back stage. And this write back stage is essentially kind of like, going back and writing to your register, right? So for example, the biggest important thing is if you're looking at the instructions, you will see that essentially each stage has a different instruction. So for this particular example, I'm borrowing from the book, we'll see that, for example, in the fetch stage, we have the add instruction. In the decode stage, I have the load instruction. By the way, this is load double word because the book is using 64-bit version. So that's why everything is double. But in our case, it would be load word. This would be another add instruction. This would be a sub instruction, and this would be another load instruction. So essentially, what used to be just one instruction in the entire design now are 5 instructions, each one independent of the other, right? And that was kind of like how we're going to get the performance benefit. And another thing that you probably notice is the way that we kind of handled control signals. So as you can see, the way that we handle control signal was that we kind of still make a decision about the control signal during the decode stage. But since now I have different instruction at different stages, I need to also push this control instruction into the registers, the pipeline registers. So I'm kind of pushing this into here. I'm consuming some of it and pushing the rest into the next stage pipeline register, consuming some of it, pushing the rest, and then consuming this part as well. So this is kind of like the way that we're going to handle this design. And then you see that, for example, I move this AND gate here and so on. These are all for just making sure that these stages are equally balanced in terms of the timeline, right? So this was kind of like one thing to notice. Another thing to notice is kind of the wiring for your RD. This was this part that essentially I kind of like emphasized a little bit more. So if you look into this part, you'll see that what is connected to my RD is not directly coming from this instruction. It's not like this. It's actually coming all the way from the pipeline registers, because this is the RD that is coming from the write back stage and not from the decode stage. Because given this example here, you want to write back from this instruction. So you want to get this value to be kind of stored. That's why it's coming directly from here instead of coming directly from here. Because if it's coming from here, it would have been this load, but I want this load, right? So you see that it's actually a correctness issue if I don't do this. All right. So this is kind of like was the beginning of story of the pipeline. But unfortunately, what we saw was that the pipeline, although the design is kind of straightforward, there are a whole bunch of problems that we need to fix. And the biggest problem that we had was this raw data hazard. So the raw data hazard was this problem of I'm writing to a particular register, and within few cycles, I'm trying to read it. And if you're actually looking at the timeline, you will see that essentially this instruction happens, the write happens during this cycle. Versus if I want to read it immediately, I'm expecting the value to be ready at this cycle. So kind of 2 cycles before And that's the problem, right? Because the value has not been updated. And I told you that this raw data hazard is not just between the first instruction and second instruction. It could also happen between the first instruction and second instruction, okay? And in this case, again, you will have something like you want, the write is happening here, but I want to read it here. So there are two possible kind of raw data hazards that might happen, right? But then the last thing that I said was, do we have a raw data hazard between the first and third? And the answer to that was no. The reason that this was no is this introduction of this concept that we call half cycle, which essentially we told you that you're writing in the first half of the cycle at this point, but you're reading at the second half. So if you actually look into this gray shaded area that is here and here, you will see that the write is kind of on the left half and the read is kind of on the right half. And then these two doesn't overlap. So that's why you can write and read at the same cycle if they happen to be at the same stage. So that's why there is no raw data hazard in this green part. There is a raw data hazard in the red, and there is a write data hazard in blue, but there is no raw data hazards in the green. Any questions so far? Yeah.
Can you go over that again? Why there's no hazard of green?
There's no hazard in the green. The reason for this is that, you know, if you look at this, is that I want to read X5 and I'm writing to X5, right? But if you look at the timeline of this particular cycle, this cycle here, you will see that the write happens at the first half of this cycle. So if this is a full cycle, okay, if this is a full cycle, okay, this is kind of like this, right? Oh, sorry. This is kind of like this. So if this is a full cycle, you'll see that at this point here, kind of in the middle of this cycle, this write already finishes, okay? So this write at this point, I'm guaranteeing that this write is finishes. So if I kind of make sure that my read happens at this second half of the cycle, at this low end of my clock, then there's nothing to be worried about because write already done, and now I'm reading the correct value from the register file, right? So this kind of like I'm dividing my full clock cycle into kind of two half cycles, and then I'm writing in the first half, I'm reading from second half, and that's why we don't have a hazard, right? So now then we talked about how do we fix the raw data hazards, and I explained two solutions for you. They're kind of like a simpler solution, which is stalling the processor, which means that if I expect to have a raw data hazard, I'll wait until the value is written to the register file, then I continue the rest of the processor, the rest of the execution. And then the second option was forwarding, which means that I, kind of temporarily forward the value of the previous instruction to the next instruction. So the first option, the stalling, was done by this concept of what we call bubbling. So if I have this add instruction here, that's kind of writing to this X19, and if my immediate instruction after that is the sub instruction, instead of like executing this immediately after this, I'm adding these two kind of delay slots and adding what we call a bubble. And then at this point, now this write back as this stage and this decode is this stage and this works. So if I kind of like, delay everything by 2 cycles, then I'm fine. And this is how we are doing it. So essentially, for example, if you look at this, an example like this, that you have an add instruction that writes into X5, and then the sub instruction that reads X5. And then let's say, for example, the third instruction is a load that doesn't have any sort of dependency between any of these instructions. In a regular scenario, I had add here, add here, add here, add kind of going here, and add here. So this is kind of like, if this is the cycles, the adds kind of like goes like this. The sub would have been like this, right? But what we said is that, we're going to have, and this would be load. So we said that at this point, we're going to have a raw data hazard because sub wants to read, but this value is kind of written at this point. So we're going to have a raw data hazard. So what we are doing instead is that we are adding these two no-ops in the middle so that this would be add. This would be sub, and this would have been load. And then what we are doing is that at this cycle, I'm not moving sub to the next. Instead, I'm putting a no-op here, putting a no-op here, I'm putting a no-op here. And again, since this hasn't been finished, I'm putting another no-op here. I'm putting another no-op here, another no-op here. And then again, here I have my load. And then at this point now, since this is done, I can then let the sub go, which means that now the sub goes here, the sub goes here, the sub goes here. And now the load basically was here. Now the load goes here, the load goes here, the load goes here, and so on and so forth, right? So this is how we're gonna basically execute this instruction, right? So the load was here and now goes here and here, right?
So if the third instruction has no dependency with the first two, can you just like replace the no-op with that?
So the question is, if this one does not have any dependency between these, can I run this here? You can, and that's the concept of out of order execution, actually. But here, remember that we want to stick to the order of execution. So basically, this is the original order. So I want to make sure that things happens like this. Because if I move this here, then a whole bunch of new problems will arise that we're actually going to talk about next week. So they're doing it naively can create lots of problems. Yeah.
Why is load word before the read? So
Which were?
why is load word?
The question is why there is a load word here, right? So that's your question here.
Yeah.
So like think about this, right? So when I'm moving the sub to my decode stage, I'm pushing the load into the instruction memory stage, right? That's how the pipeline works. So the moment that the sub goes to the decode, then the load comes into the fetch, right? But now, since I have the hazard problem, I don't let sub to move forward. As a result, load also stay put into the fetch. So basically, if you can see like this part, you will see that for 3 cycles, load kind of stays in the fetch stage, in the instruction memory stage. And at this point, only once I let the sub go forward, now I can also let the load to move forward, right? Yeah.
What would you do if you have like three no-op? Would you be able to next instruction after
So if I needed 3 no-ops?
Yeah.
In that case, so the question is, what would happen if I had 3 no-ops? Then it's just I'm adding another one of these here. So just things goes one step down. So again, my load and sub stays in fetch and decode. I'll just push another no-op into the pipeline. I can keep doing it. I can do it for infinite number of cycles, right? Keep load and sub into my fetch and decode. Just keep pushing bubbles into execution right back in memory until things are kind of the steps that I want. Yeah.
If we were to draw this, so we would draw the first and the third, but so would we draw the middle two, or would we just say, okay, for the sub instruction, we have IM where instruction 2 currently is, and then just put 2 bubble spaces and then the rest of the instruction?
Oh, in terms of like how do you write this? You can either do it this way. So I think the microphone captured your question, so I'm not going to repeat it. But so basically, yeah, you have like, for example, in your homework 3, the way that I ask you to do it is like doing like this. So if this is fetch, decode, execution, memory, write back, I ask you to do add, and then in this case, Actually, no, let me do it this way. So this was fetch, decode, execute, memory, write back. No, this was, sorry. This was cycles, so this is 1, 2, 3, 4, 5, 6, and so on. So these are the number of cycles. And this is your add, this is your sub, this is your load. In your homework, you should write it this way, basically, that you do fetch, decode, execute, memory, write back. For this one, you do, so this doesn't start here, it starts here, fetch, decode. And then since you have to kind of stall, you kind of do something like this, and then do execute, memory, write back, and so on. And for the load, the fetch stays here, stalls, decode, execute, and so on and so forth. So this kind of like this line here says that decode stays the same. Or another methodology you can use is that decode, decode, fetch, fetch. Right. This is also makes sense. Either of these. All right. Say it again. So essentially this, so the question is that could you put knobs here kind of and make this longer? You can, but you don't need to because essentially this means like if you're repeating the same thing means that you are stalling the processor. So you don't really need to show the knobs. It's just kind of make this messy. So that's usually the notation that you should follow. Okay. So how do we implement this? Basically, how do we implement this no-op? If you remember, I told you that I'm actually adding this additional mux. And what this mux does is using this, what we call a hazard detection unit. The responsibility of hazard detection unit is basically detecting if we need to stall the processor for any reason. And if we do, we do three things. First of all, we're going to add this mux in the path of the controller. And what this mux does is that instead of sending the actual control signal, it's replacing it with a 0. So all 0 instructions. So I'm kind of sending the actual control signal. I'm passing through zeros to my pipeline. And this goes through the execution, memory, and write back. This is where we're going to insert my knobs. The additional two things that we do, so this is the first thing that we are doing. The additional two things that we are doing is these two additional control signals. This is one is this PC write, and the other one is this IDIF write. So what are these two? These are write enables, okay? So these are write enables, which means that they're telling the registers don't update, because if you remember in this example that I showed you here, what basically we are doing during the stall process, we are keeping these two instructions in the same cycle. So load stays in the fetch state and sub stays in the decode stage, right? So basically you're telling the registers don't update because you want to keep this in the same stage, okay? So how do we do it? We do it using this trick here, that we're adding these two write enables, and we make them equal to 0. When the write enable is 0, means that this value won't get updated, this value won't get updated, which means load stays here and the sub stays here until we'll tell them to now you can move forward. Question?
That only stalls both the load and fetch stages, right?
The fetch and decode, yeah.
It's like a hazard where you only need to stall for one cycle.
So the question is, what if you just want to stall for one cycle? For these particular scenarios that we have in our design, you always stalls for both. You stall both fetch and decode. If you had, for example, if there is another design that you would have wanted to do this, then you probably would have had another signal, something like this. Or you could just basically do the simple things that this becomes equal to 0, but this becomes equal to 1. So you stall 1 and then you let the other go, right? So it's the same story as here, right? The write enable for these are equal to 1. I'm just pushing the bubble inside. So you probably need to push some bubble and then let it to move forward, right? But essentially these are control signals, so you have full control over them, right? Okay. So going back to this was the first option that we talked about, stalling the processor, but of course we can do forwarding. The good thing about forwarding is that you don't need to stall, so your IPC or CPI doesn't impact it. So how do we do the forwarding? We either forward from beginning of the memory stage to the ALU. So if there's a scenario like this, and have the correct value of X5 here, so I can actually forward it from here to beginning of my ALU. So I read the incorrect value here, so I fix it by forwarding from here. There's also another option for forwarding when there is a dependency between this instruction and this instruction. In that case, I'm forwarding at the beginning of my write back stage, again, to the points for the ALU. So I read wrong value here, so I'm fixing it like this, right? So this is how the forwarding happens. How do we implement this? You're adding these two muxes at the before the ALU stage. Remember, I told you that we are forwarding at this point here. This is basically this design here, right? So I'm adding this mux, that these two muxes are essentially gets the correct value, like the default value, and then these two values. And then if you look at this, where these two values are coming from, one of them is coming from here, and one of them is coming from here. This is the beginning of the mem stage. This is the beginning, this is the beginning of the write back stage. Again, if you look at this is one option for forwarding here. And then this is the other option for forwarding. This is how we are doing it. From here or here goes into this muxes. Who control this muxes? This control signals that goes into this forwarding unit. So this forwarding unit is basically check some condition, this I'm going to describe. And then this forwarding condition basically tells whether you do your default operation, which is this signal, or whether you need to forward from mem, or whether you want to forward from write back. So one of these can help you to kind of make a decision, right? The important thing is that, as I said, you either forward from mem or write back. So you either have this, or either this signal or this signal. And then, as you can see, the forwarding could happen for either of the source registers. So either this one, or even both of them. So sometimes you need to forward both registers. So that's why you have two muxes, okay? There's this mux and there's this mux. There's this control signal called forward A, and there's control signal called forward B. So these are independent from each other. So you can forward to one register or to another register or to both of them if you want to, okay? So what are the conditions? The conditions, as I said, is if the RD of the instruction in the memory stage is the same as the source of the execution stage, or if either RS1 or RS2, or if the RD of the write back stage is similar to the RS1 or RS2 of the execution stage. And you also need to check the reg write, because you want to make sure that this is indeed an R-type or I-type instruction. So again, if you look back at this is how we kind of implement this. So this is like the RD, this is RD, this is RS1, this is RS2, and this is how we actually make this decision, okay? So we also talked about this fact that forwarding, forwarding, of course, helps to prevent stalls. But one thing that we saw was that this is not always true. One example was for the load instructions, because for load instruction, we saw that, forwarding alone doesn't help. Why? Because of this scenario like this. If I have a load instruction and then a sub instruction immediately after, I'll see that the correct value of X5 is available at this point. But what I want to do is at the beginning of that part. So remember, forwarding before was happening from here to here, but now you need to kind of forward from here to here, which is not going to happen because that's the end of that cycle and that's the beginning of that same cycle. So I cannot do forwarding for loads. What I need to do is that I need to stall for one cycle and then forward from here to the ALU state. So basically I'm forwarding from here to here, right? That's how we're going to do so I stall for one cycle and then forward. So that's the difference between what we call a load use data hazard and regular R-type and I-type data hazard. So this is the condition for load use. As you can see, this is basically telling that if the RD of execution stage is similar than the ID of the source, source of the ID stage. The reason for this is that you need to stall. Since you need to stall, you can only stall things when you can stall things if as I showed you here at this stage, okay? So I need to detect that there is a load use hazard at this stage. That's why I'm checking the control signal at the decode stage and not at the execution stage. That's the difference between forwarding that is happening during the R-type, I-type instruction and load use instructions. Because I need to know that I need to stall, so I need to check the conditions here, okay? So if I show you the implementation, it will look like something like this, that essentially I have this hazard detection unit that takes this control signals and issue a stall if I see a load use data hazard. Then afterwards, I can do the regular forwarding once things move into the next stage. So in addition to forwarding, I do the stalling. So that's why you have both your hazard detection unit and forwarding unit together. And this will help you to kind of do both stalling and forwarding at the same time. If you look at the conditions, as I said, for load use, this is for load use, okay? For load use, I'm checking what? I'm checking if the RD of execution stage is equal to RS1 of the decode stage, okay? So if you look at into the data hazard, I'm taking these two signals, which is RS1 and RS2. These are these two. I'm pushing this into my hazard detection unit here. And then another thing that I'm checking is the RD of the execution. So I'm taking this RD of execution and push this also into my data hazard here, okay? So RD of execution, RS1 and RS2 of decode, both of them goes into my data hazard detection unit. If it detects that these two conditions are true and mem read is also equal to 1, this is also another input to my data hazard detection unit, then I'll issue a stall, right? So how do I do that? I issue this thing here and then I kind of push forward one stall. And then if you look into the forwarding, you will see that basically the forwarding is if my mem, the RD of mem or RD of the write back, these are these two signals. This is one, this is another that goes into my forwarding unit is equal to RS1 or RS2 of my execution unit. That's the difference. So RS1 and RS2 of my execution unit, these two signals also goes into my forwarding unit. So notice the difference between hazard detection and the forwarding. That's the way that we do these things, okay? In that case, I'm issuing this forwarding signals, okay? So hazard detection unit issue stall cycle, forwarding unit issue forwarding. The conditions for each one is different because one needs to do forwarding, the other one needs to do the stalling. Okay, this is how we fix the raw data hazard in our processors. Any questions? Cool. What about branches? Let's have a 4-minute break and then come back and talk about the branches as well. All right, guys, let's talk about the branches as well. So what was the problem with branches? The problem with branches was, you know, you have to kind of jump, right? So you have to jump from different part of your different part of your memory to the other parts of your memory. And this unfortunately kind of means that you kind of have to skip some part of your system, right? And if you do the pipeline is kind of doesn't understand jumping. It's just keep kind of pushing new instructions into your pipeline one after another. And as a result, if you kind of at some point decided that, oh, I need to jump, these kind of things that you're kind of pushing into the pipeline needs to be kind of get rid of somehow, right? So you need to kind of find a way to fix this issue. So again, how do we fix this? There are two solutions for this. One is through the stalling, and the other second one is kind of something like forwarding, but it's called speculations. It's not forwarding. Forwarding doesn't help in this case. But what we're going to do is that we're using what we call speculation. So how do we stall and how long should we stall? We talked about this three W questions of when, whether, where, and whether. And we figure out that basically this kind of like weather parts is kind of the side that is going to be 3 cycles that we need to stall the processor. Okay. The second option is prediction or speculation. The question becomes that, okay, what should we predict? And then there are 2 options for prediction, right? So you can always predict always taken, or you can predict always not taken, either of these 2, right? For now, simple. Later on, we're going to talk about the dynamic option as well, but each branch has 2 outcomes, right? It's either taken or not taken. As a result, you can predict always not taken or always taken. And then we start with like thinking about which one is easier, and we found that not taken is actually much easier. Why? Because of 2 reasons. The first one is not taken means that your next instruction will be PC+4, and you already have that. This is how your normal operation of your pipeline works. So that's one good thing. And the second thing is that your not branch instructions also always do PC+4. So because of these 2 reasons, it's kind of much easier to do not taken prediction. Okay, and that's what we're focusing for now. But then later on we're gonna change that. And then so we're gonna go with prediction and predicting not taken. Okay, so far so good. But there is a kind of minor issue, and that is, what if we actually make a mistake? What if we mispredict, right? What if we predict not taken and it's actually taken? And then we introduce the idea of flushing. That is, like we kind of read things and we need to get rid of those instructions. So example is, if I have a branch equal here, so the branch goes here, goes here, goes here, goes here, goes here. Then I read I1 here, I1 here, 1 here, 1 here, and 1 here, and then 2, 2, 2, 3, 3, and so on. And then when do I know that I made a mistake? I know at the end of these cycles, right? So once things move into this cycle, I need to flush things. So I basically need to flush this, I need to flush this, I need to flush this. And at this point, I need to fetch the correct instruction here, okay? So this should be the correct instruction here. So I need to get rid of whatever I put into the instruction memory, so data memory, into the ALU, and into the decoding stage. I need to get rid of all these 3 because I know the outcome of the branch at the end of this cycle or the beginning of this cycle. So how do we do that? We are introducing, so this was basically our initial design for hazard detection and forwarding. We are essentially introducing this additional kind of muxes that basically what it does is that continuing doing what we did here. So we're basically saying that, okay, remember this was the kind of the method for flushing things, for kind of inserting bubble here. So let's do this for this cycle, and this cycle as well. Okay, so we are basically saying that, okay, at this point, for example, here it was I1, here was I2, and here was I3, right? And I need to flush all 3 of them. So what I do is that instead of pushing I3 to the pipeline, I'm replacing it with 0. So at this point, I'm kind of flushing I3 and I'm replacing it with bubble when it goes to this cycle. Same story when this goes to here, I'm basically replacing it with this mux. So I'm pushing a bubble here. And then same story for this one, instead of pushing this, I'm pushing a bubble here. So as you can see, I'm essentially replacing my controller signals with 3 muxes, 1 here, 1 here, and 1 here. And then you see that this control signal is called ID flush and EX flush that creates the flushing for decode, execute, memory, and write back. So this is in addition to all things that we have. So we still have the flush, IFID, and all those things. But here now I need to flush things that I'm reading to this. And then another thing that I need to do is that if I need to flush the fetch, I also kind of like, put this IF flush as well. So I'm flushing here. This is for my decode. This is my execute. This is my write back. Sorry, this is my memory. This is my write back. And then another thing that I need to do is that I need to fetch the correct instruction. So this is also needs to flush this instruction from reading the incorrect instruction from here to here. Because if you go back here, oops. if I go back here, at this point, I would have read I4, which is also incorrect instruction, right? So I need to make sure that this is actually I correct, whatever that is, which is not I4. So this is why I also have this I flush things here. That's kind of like make sure that I'm not pushing the incorrect instruction from here to here. Okay, that's kind of the idea of all these 4 flushes that we do. So we are replacing incorrectly fetch, decode, execution, and memory and write back instructions with bubbles, basically, right? And then these are all happen again with hazard detection unit, okay? The hazard detection unit is the one that detects that there are these problems, and then it's kind of inserting the bubbles or stall. It's the flushing, you can think about it as some form of stalling, right? So it's kind of pushing this into the pipeline. So this was kind of the baseline design, that the design that I described to you, and I don't want to do any sort of prediction. I'm just doing a not taken prediction. I make a mistake, so I need to pay the price of 3 cycles, right? But now we also talked about this, that what if we don't want to pay 3 cycles penalty? Maybe we can do something better, and maybe I can resolve the branch in the decode. So instead of resolving at mem, I want to resolve at decode, okay? So in order to do that, I explained it last time that I already know the when part, but I need to know the where and whether part, okay? How do we do that? We compute the offset calculation and bring that kind of adder into the decode stage. So we add this kind of ALU for this. And then we also do the comparison between RS1 and RS2 and add an additional comparator into the decode stage, okay? So this is basically the design. I'm adding this comparator, which is kind of comparing RS1 and RS2. And I'm also adding this part. It used to be here, now I'm moving it to here. And with this, now I have when, where, and whether answers. So now I can resolve the branch during the decode stage. Okay, so that's all I need. And then the beauty of this is that if I have this, what used to be like this, that I need to flush here, here, and here, now becomes something much simpler, like this, basically. Oops. So much simpler like this, okay? That I can, as you can see, that I no longer need to flush things here and here. So these things are gone now. I don't need them anymore because I resolve things in the decode stage. So basically what I really need to do, sorry, I keep making this. What I really need to do is just this 1 mux. Okay, so this used to be 3 muxes here, 1 here, 1 here, and 1 here. Now I have just 1 muxes here, okay? So I just need to, flush 1 instruction, yeah.
Does not make the decode latency longer than all other stages?
Question is, does that make the decode latency long? It makes it longer, but not longer than the others, because still this part is much longer. So if this used to be, for example, T1, now I'm adding an additional delay of D, but this is still much smaller than Tmen, okay? So I'm still okay, yeah.
So it's also the end of decode, not the beginning of execution.
Say it again.
Like the branch resolved at the end of the decode.
Yes, at the end of the decode.
Not the beginning.
Yeah, so this at somewhere in the middle of the code, basically, right? So that's why right away that if you made a mistake and you need to push just 1 bubble to stall 1 cycle.
Yeah, so I think in earlier lectures you said the equals, so the equal sign on the right of the registers, that was where the new kind of branch equivalent thing was.
Yeah. So this is a more generic, is a comparator, because if you have less than, greater than, and all these other branches, this is all resolved here.
Okay, but speaking generally, the output as well is not drawn, but
Yeah, it goes into here,
okay.
right? Because that's where you want to know that we made a mistake. Yeah.
Can you explain again why we only need 1 mux?
Because if you resolve things at decode, you just need 1 side. So the question is, why do we need just 1 mux? Because you just need to push 1 stall. You just need to flush just 1 instruction, right? And that instruction is that's why you just need one lines. You just need to stall for 1 second.
Can you repeat again about finding the code?
Yes, so what do we want to know? We want to know whether RS1, for example, is equal to RS2 or not, right? For branch equal, for example. What is branch equal? The branch equal checks whether RS1 is equal to RS2 or not. Or for example, if BLT, you want to see if RS1 is less than RS2 or not, right? These are the checks that you want to make. So these checks used to be at this stage. So we use ALU at the execution stage, and we use this branch instruction at the mem stage to fix this, right? But what you can do here is, if I kind of, instead of using this, now if I add this comparator here, then I know the outcome at this stage, right? So I know it here. So instead of using this, I'm adding this here, and then that helps me to kind of resolve the branch.
I think you also have so during the decode stage, we want to basically have all the inputs ready for the hazard detection unit to know if it's a hazard. And then we also, so by the end of the cycle of the decode, the hazard detection unit has all the inputs and sends out all the correct control signals flush already. So then on the next cycle, the IFID stuff is going to flush also. You're going to have to extend the cycle a little bit, or if the ALT, I guess if the data memory access is long enough.
I'm not sure if I catch the question. So yes, we have all the control signals at the end of the decode stage. So when it's pushed to the next stage, then we can use this correct instruction. The only thing is that I need to kind of flush one instruction that was used to be in the IF stage, and now it needs to go to the decode stage, and that's where we're going to have this kind of IF flush that goes here. Okay. The rest of the things just continue as normal. That's why I kind of got rid of these three, because I no longer need them, because I no longer need to flush things from execute. I no longer need to flush things from memory, and I no longer need to flush things from write back, because now I know that the correct instruction is there. Let me actually give you this example, then I'll come back to the questions, okay? So let's, for example, have something like this, okay? I have a sub, I have a branch, and then I have a bunch of instruction, and this branch is going to jump to this instruction at 72, okay? So I'm going to skip all of these instructions in between and jump here, okay? So let's say that this branch is going to be taken. What will happen? So this is kind of like our pipeline stage at this moment. So I have my sub, I have instruction before sub at the memory and write back, I have my branch, and I have my AND here. So how do I get that? So this is instruction before sub. This is 2 and 1. So this would be at the write back stage. This would be at memory stage. This would be at the execution stage. This is at the decode stage. And since we are doing not taken prediction, this will be at the fetch step, right? So this is how it works. So branch decode, and here, sub here, before 1, before 2, right? So at this point, we predicted not taken. That's why we fetched this AND instruction, right? But we made a mistake. This branch is supposed to be taken. So what are we doing? We are pushing this branch to let this to move forward. We'll let this sub to move forward. The 2 was already finished. So 1 goes to the write back. And we used to have AND here, but since this is a not taken, I need to flush this. So I need to push a bubble here. How do I do that? I use this IF flush things to push a bubble. So essentially now I put the bubble into the decode stage, okay? And now I'm going to let this bubble to move forward. And now I fetch the correct instruction, which is this load instruction. Again, going back to the example, this was the AND instruction. This is the incorrect instruction that I need to get rid of. And this is the correct instruction that I need to fetch, okay? So again, looking at this, branch was here, AND was here, sub was here. Now the sub goes here, branch goes here. Instead of pushing the AND here, we're substituting this with the bubble using this IF flush. And now I'm fetching the correct instruction, which is the low. Does that make sense? Question?
So if you're comparing, at RS1 and RS2, right?
Mhm.
What if those values are dependent based on forwarding? So we don't have them.
Yeah, that's what I'm going to actually show in the next slide. But the question is, if I have this and wants to do the comparison, if these two are actually needs to be forwarded here, what should I do? And I'll actually explain this exactly in the next slide. Any other questions? All right, so let me finish this. So there will be exactly this scenario that you're saying. And so imagine a scenario like this, that I have add x1, x5, x2, x1, which means that I'm going to update the value of x5 here. But immediately after that, the next instruction, I'm checking whether x5 is equal to x4. And this is a similar scenario as any other raw data hazards that you have. So how do we fix this? If we didn't have this, and we use the regular ALU for the checking, this forwarding would have fixed this issue. So we didn't have any issue. So if we had kind of like resolved the branch during the MEM stage, we didn't have raw data hazard. But since now we are moving things to the decode stage, now the forwarding happens just one cycle after, but I need the data here. So what would I do? I basically will do the forwarding one cycle back. So essentially whatever I have here, I push it to here, okay? So I do add the mux here and then do the forwarding basically one step before, because now I need to kind of fix this issue. So everything that I have here, I kind of push it back to one stage. I'm putting it at the end of the decode stage, okay? This way I'm gonna fix this issue because the forwarding is basically checking this. And of course, all these checks needs to move one step here. So basically everything here, this signal, everything is shifted by one cycle to the left. So now I'm checking here and checking here, and I'm forwarding from here to here and forwarding from here to here. All right. So all the things that you have, just imagine happens just one cycle before. Okay. Everything one cycle to the left. Okay. That's how you're going to fix the issue of raw data hazards for branches when you are also fixing the decode. Does that make sense?
Yeah, but what does it mean by moving one branch to the left?
No, not saying moving one branch. I'm talking about moving this mux to here. Okay. So you move this mux to here, and as a result, all of these signals is also one cycle before. So what used to be like this is now going to be like this. So instead of forwarding from mem to execute, you're forwarding from execute to decode. And instead of forwarding from write back to execute, you're forwarding from mem to decode. So everything one cycle to the left. Does that make sense? And then for load use, you're gonna still have the same problem, so you have to stall for one cycle. Okay, so remember for load use, I had to stall and then forward. Same thing happens for the branches. You have to stall for one cycle and then forward. Okay. So this would be your design before doing this hazard detection. As I said, this will move here, this will move here, and then all these control signals move with it. Okay. And then everything else stays the same. So if you have to stall for load use, you still stall for the load use. If you need to forward, you would forward. Nothing changed, but it's just the way that you forward happens one cycle before. Okay. So that's kind of it. So again, if you remember, so to kind of like, summarize, you have various different options for branches, okay? So you either stall at memory stage, you can stall at decode stage, you can predict not taken at the memory stage, or you can predict not taken at the decode stage, okay? So these are kind of 4 options that you're going to have. Depending on each one, the number of stall cycles and forwarding might change. So just be careful about the differences between them. Of course, the fastest among these is this one. The slowest among these is this one, right? So this is what we usually do in a modern system. we resolve at the decode and we predict not taken at the decode as well. Okay? Any final questions?
You know how when we have the offset being shifted by 1 to the left, which we can multiply by 2?
Mhm.
How does that affect when we make our assembly? So like, how do we know, how do we calculate which is the right instruction to jump to? Like, for example, I know I want to jump to 72, right? And how
Mhm.
would I write that? Do I have to like subtract from the label and then divide by 2 to get the right number that I want for the assembly code?
So-
Yeah.
So this, yeah, so the question is, how do we do this? So remember that this number is needs to be shifted by left, right? So you multiply this by 2, and then you add it to your base register, which is in this case, this is your PC basically. Your base register is PC. So multiply by 2 plus the PC, that gives you the address that you need to jump
So I mean, like, for example, when we're implementing a branch,
to.
when we take in that binary, is this what the binary shows that it shows us the offset, and then we have to compute it by like multiplying by 2, and then that comes up with the right instruction?
I think your binaries has the actual labels, if I remember, like your assembly codes. But yeah, if it's just a regular number, yeah, that's how you should come. I think your assembly codes has actually says like label and whatever.
I just remember, I think in machine code. is the one-
Yeah, in the machine code, this is the number that goes into it, so that's how.
Looks like again.
Because the immediates are the immediates are between, so immediates are 12 bits, but the way that you actually put it in the machine code, instead of putting 0 to 11, you put 1 to 12, right? So everything is, and then you always like 0, like put 0 at the 0th bit, because you don't want odd addresses, right? So you don't want to kind of waste 1 bit for nothing. What I can do is that I can move everything by 1 bit to the left and then have a bigger range to jump, right? So if I have 12-bit number versus 13-bit number, I can jump twice as much, right? So that's how we encode this basically. It's kind of like a minor optimization, but instead of being 0 to 11 and knowing that always this 0th bit is equal to 0, what these guys are suggesting is you write it this way, but in fact it's actually 1 to 12, and then you add a 0 on the right. Does that make sense?
Let me, like you're writing the machine code, like you asked. If the 16 there, do we interpret that as the calculated one, or like?
If it's a label, it's a calculate one. If it's 16 like this, then you multiply by 2 and then add it to your piece. The question is why we're not shifting by 2 bits. So because we want to support 16-bit instruction as well. So you want to be just even, but not multiple of 4. So you want multiple of 2 and not multiple of 4. If you didn't have compressed instructions, then you always do 4. So in that case, you shifted by 2. So if you actually see some older version of the book, you will see that it says shift by 2, left shift by 2. That's why, because at that time we didn't support compressed instructions.
So when that 16 goes into machine code, the bit 1 to, the bit number 1 to 12 is just 16, and we add a 0.
All right. So we don't have time to go through the branch predictor parts. That's actually good because now you're not confused. I want to also quickly mention the role of the compiler. As I said, this course is not about the compiler, so we don't really talk about the compiler. But the compiler can help you a lot with all of these things. So one big thing that compiler helps is what we call the delay slot. So remember, I told you that if you have a load use, we need to stall for 1 cycle. So if the compiler can somehow reorder instructions for you without actually making any issue, then we kind of like won't have this issue of load use, right? So if I have like a load here and an add here, that this add is dependent to this load, I need to stall for 1 cycle, right? But if I have a load here and then some other instruction here and then add here, then I don't need to stall because this instruction is independent from these two. right? So if somehow compiler can reorder things without really messing things up, then we can always kind of get rid of this 1-bit stall cycles. We can always do something useful during the cycle, so our CPI remains 1 or remains 4, whatever. Sorry, remains 1. But this is something that's, the reordering may not be straightforward for the compiler, and I'm not going to describe how the reordering will happen. What we will describe later next week is the hardware can also do this reordering for us, and that way we can actually get a significant performance boost. Another thing that the compiler can help us is that if you're going with this not taken approach, we can also do something to increase the chance of not taken. How? Basically, the way that we kind of put these blocks next to each other, the compiler can know, for example, whether it's more likely for the not taken branch to be to the branch or not. So basically, the way that we put the instructions right after another, we can put and move the blocks around so that the chance of not taken is increased. And the lastly, another use of the compiler is what we call loop unrolling, which means that instead of having branches, if I repeat, for example, if I have like something like a for loop, right? And then do things here. So basically what this is like sequence of instruction, a branch at the end, right? But if I copy this multiple times, then I'll get rid of the branch, right? So I increase the code size, I increase the number of instruction, the static number of instruction, but I get rid of the branch as a result. So that increases my performance, because if every time that I make a misprediction, I need to stall for 1 cycle, this unrolling actually going to help. Okay. So next time I'm going to talk about this branch predictor, and you're going to see how these things are going to help us. All right. Thank you.
Have a question.
Hey.